Hi, thank you. Yeah, I'm Derrick Quinn. I'm coming from Cornell. I'm here with my colleague Ezgi'25. Today we're presenting our work on accelerating dense retrieval via algorithm-hardware co-design. And this is something that we've been working on with colleagues from University of Virginia and Carnegie Mellon. It's called DReX. So first of all, at a high level, for why this dense retrieval problem is important, dense retrieval is really used to implement semantic retrieval, which is based off of meaning rather than things like keywords. And it powers a lot of apps, including some traditional apps that I've got here on sort of the right-hand side. But we really focus in this work on retrieval augmented generation, things like chatbots and stateful agents. Dense retrieval is very useful for that. This is an example of a sort of representative dense retrieval pipeline, or how it integrates with a retrieval augmented generation pipeline. So the system will take an input, and then it will use a dense retrieval phase where a dense retrieval model scans a vector database using nearest neighbor search, returns a list of k documents, k is a number like 10, and gives those to a generative model, like a large language model, which then proceeds to the generation phase and generates the output. This is looking at that vector database in a little more detail, right? We have all of these documents. The vectors are semantic vectors, and they exist in this sort of high-dimensional space. And when a query is received, we also convert it to a semantic vector, and we want to scan these documents using a similarity function. It will be dot product. I'll show you later. But essentially, we'll scan a subset or potentially all of these document vectors and collect the top k documents. The naive way to do this is via exhaustive search, where you essentially scan all of the documents just iteratively, and then based off of that, collect the top k after you've scanned everything. But what's actually used in practice is approximate search, which lies on this sort of accuracy and speed trade-off curve. And in fact, exhaustive search is here too. It's sort of the most accurate you can get, but also the slowest you can get with a given data set. Whereas the rest of the approximate search schemes form this Pareto frontier of, you can get high speed by sacrificing a little accuracy. One thing that we claim in this work is that there's some shortcomings with existing approximate search. Now, this is for a question answering RAG application using state-of-the-art language models and approximate search schemes. And we look at time to first token in terms of this is like latency that's relevant for user applications. We see a few things. One is that retrieval with a state-of-the-art approximate search can make up a substantial portion of this time to first token. And the other thing is that we see as we increase the number of documents that are fed to the generative model, that massively increases latency. And so if we can accelerate retrieval, we can cut down on the retrieval part, of course, but if we can make generation or the retrieval higher quality and reduce that number of documents, we can accelerate generation as well. That's really the motivation here. To that end, what we contribute in this work is an algorithm-hardware co-design approach for dense retrieval. Specifically, it's sign concordance filtering, which is a novel near data processing friendly ANNS algorithm, and then an accelerator called DReX, which uses in and near memory processing to accelerate dense retrieval. As you can see on the right here, this is looking at accuracy and throughput. Compared to CPU and even GPU-based approximate search, we can achieve dramatically higher speed for the same accuracy target and, of course, accuracy for the same speed target. As for the rest of this talk, I'll take you through sign concordance filtering and what we do specifically, and then Ezgi will take you through architecture through the evaluation. So I'd like to touch on the bottleneck in existing approximate search systems. This is a roofline model for a CPU, looking at a state-of-the-art approximate search scheme using HNSW, looking at arithmetic intensity and performance. We sort of see that for even 5 different data sets, these are clustered right around a low arithmetic intensity, so in the memory bound region, sorry. And when we'd like to improve performance here, we'd like to move these up. So one thing is we can't move the existing algorithms closer to this roofline, essentially make them more efficient due to complexities with the algorithms themselves, as well as very random memory accesses. And then if we want to improve the roofline, adding on to that, It's challenging because these algorithms are very communication heavy. Like I said, they're complex. And so this is going to be something that it's hard to apply near data processing techniques today and do this sort of in a cost-effective way. To that end, we propose sign concordance filtering. And I'll get to that, the exact way we do that in a second, but before, just a little overview of what we try to do with dense retrieval in a little more detail. When we receive a query, in this case, a mammal, which is in red, and we want to know how similar it is to a document, in this case, a cat, we're trying to find how small this theta is between those. Actually, small theta, more similar, that can be found by finding the maximum dot product between the query and a document vector. And so you can see that a frog has a much bigger angle and it'll be a lower dot product, and a car is a completely different thing, not even an animal. So the angle is a lot larger, the dot product's a lot smaller. And we'd like to be able to filter out some of these documents that we know are irrelevant so that we don't have to do this full dot product. What we can do is look at the sign bits, essentially, or the signs of each dimension here. So mammal is positive in the x direction, which means that anything negative in the x direction is a lot less likely. Same goes for the y direction. Anything negative in the y direction is less likely. So we'd like to be able to take the car and not compute the full dot product, not need to look at that. And we can actually do this, again, by looking at the sign bits. In a little more detail, what we do is we will store bit vectors essentially for the document signs, and then set a threshold of the number of signs that need to match between a query and a document to qualify for full reranking. And then when a query is received, we'll scan the documents, look at the bit vectors, and re-rank only the documents that pass the threshold of matching signs. As for how we do that in hardware, or in a second, this shows the effectiveness of sign concordance filtering on just algorithmically. We're looking at the search space reduction, right? So 10 on here is 10 original vectors to 1 that we actually re-rank. And what we see is that we can achieve 95% accuracy, retrieve 95% of the relevant documents by only looking at 1 out of every 10, at minimum 1 out of every 10 documents. And for high dimensional vectors that are more representative for RAG, which I've colored in red here, it's actually more like 1,000x, 1 out of every 1,000 that we actually have to re-rank. So this algorithm does work quite well for filtering. As for how we do it in hardware, Ezgi will take you through the architecture, and that's next.
Hi everyone, I'm Ezgi and I'll be covering the rest of the presentation, starting with the architecture. To leverage the algorithm, we design an accelerator called Dense Retrieval Accelerator, or DReX. And DReX is composed of 8 LPDDR packages. So it has the total capacity of 512 gigabytes, and it functions as a CXL memory expander. Therefore, it is byte addressable through cxl.mem, and it is controlled via cxl.cache. It can also work with CPU and GPU in a system, and it uses both in and near memory processing. Therefore, it is a hybrid accelerator. Building on what Derrick explained, the process is composed of 4 main stages, and I'll try to explain those stages by linking with the system. So first stage is initializing the dense retrieval accelerator by invoking it from the CPU and writing the necessary information to the DReX, such as query or the algorithmic threshold. The second stage is filtering. So as Derrick explained, filtering stage uses the sign bits of the embeddings, and it creates a bitmap which indicates whether the set of embeddings are included in the search space or not. Since the process data is way more than that the data sent to the next stage, we design this stage near bank using the pin filtering units. By that, we leverage from the embarrassingly parallel structure of the filtering phase, whereas we avoid the unnecessary data movement. The third stage is calculating the similarity scores. And since this is a more complex operation than filtering, as it involves floating point multiplication, we implement this stage near memory by using near memory accelerators. And NMAs, they fetch data from the memory based on the bitmaps that PFU sent and calculates the similarity scores. They also maintain the partial top K, which brings us to the final stage, which is ranking. So each NMA sends its own partial top K list to the CPU, and the final ranking happens in on the CPU. So in this slide, you can see the more detailed internal structure of PFU and NMA. PFU is on the right and NMA is on the left. I'm going to skip this part for now, but you can find a more detailed explanation in the paper. So we simulate DReX by using theorem sim3, also with the results from our RTL synthesis, and we combine those things in a custom timing simulator, and we compare the performance of DReX with the existing ANNS implementations from MetaFace library on CPU and NVIDIA CUVS library on GPU. During the experiments, we use Intel Xeon CPU with the NVIDIA H100 GPUs. We evaluate 5 different data sets, and we set the accuracy target over 95% for top 32 documents. So as you can see from the graph, DReX outperforms the existing solutions. So we evaluate, as I said, 5 different data sets and compare its performance against different configurations, such as best performing ANNS CPU implementation and best performance ANNS GPU implementation, as well as prior accelerators such as IKS or ENA. And we report the geometric mean of query per second, and as you can see, we obtain a 64x speed up over the CPU baseline, whereas we achieve a 9x speed up over the GPU baseline. Yeah, but where does this speed up come from, right? So as Derrick explained, the sign concordance filtering is itself a competitive algorithm, but when we run it on CPU, we didn't outperform the existing ANNS implementations on CPU. So the real gain comes from the near and in-memory processing. By designing a algorithm-specific accelerator, we leverage the embarrassingly parallel structure of the algorithm, and by that we achieve a significant Pareto frontier expansion in performance. So a couple of power and area results of PFE and NMAs. So each NMA has a 15.07 millimeter square area, and its peak power is 1.07 watt for batch size of 16. And there are 8 NMAs in total per DReX. Whereas a single PFU has 0.1 millimeter square area, but per package there are 1024 PFUs, so the total area overhead per package is approximately 6.7%. Also, a single PFU has a peak power of 14 milliwatt for the batch size of 16, but under the full load with 1024 PFUs, including the memory access, the peak power consumption during the filtering per package is 18.4 watts. Yep, overall, we present sign concordance filtering, which is an ANNS algorithm designed specifically for near data processing. And to leverage the algorithm, we design an accelerator, which uses both in and near memory processing. And we obtain, on average, 64x speed up compared to the HSW on CPU, and 7x reduction in time to first token for a representative RAG application. That was all. Thank you for listening, and we would like to have if there's any questions.
Okay, please come to the mic if you have any question.